Alrighty, so I guess we can get started, right? Alrighty, so good evening, everyone. Good morning, afternoon, evening, depending on where you are in the world. And welcome to the AP Physics C Mechanics Review. So, what we're going to primarily be doing in tonight's session is um, we're going to start off with just an overview of the exam, the types of questions you'll see on the exam, and then we're going to spend a majority of the time going over actual questions. Because at this point in time, we are actually exactly a little under actually 3 weeks from exam day. So the best thing we can do, I think, together is to do practice questions. Actual questions are published from the College Board. The questions we're going to look through tonight are all from the course and exam description written by the College Board themselves, so it's probably one of the best sources I think we can use to see their format. We'll also be perusing chat throughout the evening to answer questions. I can start off with just answering Brave Ninja's question about simple harmonic motion. So simple harmonic motion, I'll just say a couple things about that. The first thing to understand is understand its definition. So its definition, first of all, is at the very basic level, when you have when you displace an object in simple harmonic motion, it's going to follow the following rules. When an object is displaced from when an object is displaced, the restoring force that points toward its direction of equilibrium position is going to be proportional to the distance it has displaced. So that's the simple definition of simple harmonic motion. And when it comes to applying that to problems, it's really just a lot of Newton's laws, primarily that. That's just a general overview of simple harmonic motion. We can go through more detailed problems later on, but that's the whole idea of simple harmonic motion. Anything you want to add on to that, Neil?
Um, no, I think you covered most of it.
Okay. Yeah. All right. So I'll start off with going over primarily just going over the exam format, and then just there's an ambulance on the road. We'll start off with going over the exam format, and then going into just weighting of the topics, and then Neil will take over with the types of response questions, and then we're going to get into actually doing the questions. So the exam this year for all of the AP Physics courses has changed in scope. For Physics C, it used to be you had to do 35 multiple choice in 45 minutes, and then three free response in 45 minutes. Now it's completely different. It's 3 hours long instead of just an hour 30 long, and you have much more time per question. So now you have 40 multiple choice questions to do in 80 minutes. So that gives you about 2 minutes per question as opposed to less than a minute and a half per question with the old format. And that will count for about 50% of your AP score. For response questions, you are now going to have to do four, but you will know the type of question that you have to do beforehand. So back in the day would be that you would have three free response questions worth 15 points each, and the topics will kind of just be thrown at the topics and like expectations will kind of just be thrown at you from left field. But now we have the types of questions which Brunel will go over in a little bit. But essentially, you have mathematical routines, which is really what it sounds like doing math. Translation between representations, so that might mean like graphs, diagrams, explaining, deriving equations, and all that stuff. Experimental design and analysis. I would say this one is probably the toughest one to get used to because you're going to be asked to design an experiment to collect data, and then you'll be asked to, for a different experiment, to linearize data. It's probably the slightly easier part. And then quantitative translation, go between equations and descriptions of just what happens. So those are the four types of response questions that you'll see. Added together, those are 40 points total, and that will weigh in at also 50% of the AP test score. And you have an hour 40 minutes for those four response questions. So the topic scope of the AP Physics C Mechanics exam really hasn't changed since the last year. It really hasn't. I mean, physics pedagogy really hasn't changed that much at the college level for maybe the past 5 to 10 years, I'd say. Depends on where, but the general way that classical Newtonian mechanics has been taught, as far as I know, hasn't changed too much. Because I mean, granted, Newton was born hundreds of years ago, not yesterday. Funny joke. Actually, no, it's not really a funny joke, but you get the idea. Anyway, so with physics mechanics, and just how classical Newtonian mechanics is structured at the AP level. Start off with kinematics, which is just how things move, or just, yeah, it's describing position, velocity, acceleration, and all that kind of stuff, kinematics. And then you get into, I'd say this is probably the meat of the course. This is going to lay the foundation for the rest of the course. Force and translational dynamics, so Newton's laws, a lot of that stuff. Then you get into work, energy, and power, also a pretty heavy topic. Slightly a little lighter is linear momentum, and then probably the hardest topic I would say for mechanics, torque and rotational dynamics, and then also energy and momentum rotating systems. Rotation's a pretty heavy chunk of the test generally. Then oscillations, which is pretty much simple harmonic motion, and then gravitation is pretty much included within energy momentum rotating systems. So that's the multiple choice section of the AP test. Everything is pretty evenly weighed, but with a pretty good emphasis on uh, force, force and translational dynamics, and then also a pretty heavy chunk on rotation. So yeah, 2, 5, and 6 are pretty well weighed. And then also work, energy, power is another one that's pretty heavily weighed. So 2 and 3, and then the combination of 5 and 6 are, I'd say, the most heavily weighed. All right, now let's move on to the types of free response questions.
So there are four types of free response questions, as you went over previously. So the first one, mathematical routines. You're given a scenario and you have to make predictions. So you have to make relationships between variables. So um, like without plugging in numbers, basically, and then you'll have to plug in numbers. And you'll have to create and use representations that describe the scenario, to help guide your mathematical analysis. So like that could be a free body diagram, or like something like that. Um, or representations that are applicable to the scenario, like sketching velocity as a function of time or some other graphing to quantities. Um, and this question is worth 10 points. And the suggested time is 20 to 25 minutes. Um, so yeah, and then the second question is translation between representations. So, it assesses students' abilities to connect different representations of a scenario. You'll be expected to create a visual representation that describes that scenario and derive equations that are mathematically relevant, and draw graphs that relate quantities. And then the last part, you'll be asked to do one of three different things. So either justify why your answers to two previous parts do or do not agree with each other, um, use their model, the representation, or mathematical analysis, or their graph to make a prediction about another situation and justify that prediction using reasoning or analysis, or use your representation, mathematical analysis, or graph to make a prediction about how those representations would change if properties were altered, and then justify that claim using consistent reasoning or analysis. This question is worth the most. It's 12 points, and 25 to 30 minutes. So um, they they expect you to allocate the most time to this question, or more time than the first question at least. The third type of question is the experimental design and analysis. Um, so you have to create a scientific procedure that can be used with appropriate data analysis techniques to determine the answer to a STEM question. The question can be roughly divided into two different sections, design and analysis. So for design, you'll be asked to develop a method in which a question about a given physical scenario could be answered. And the procedure is expected to be scientifically sound, vary a single parameter, and measure how that change affects a single characteristic. So basically, you have your um, independent variable and your dependent variable following the scientific method. The methods must be able to be performed in a typical high school lab. So basically, anything that you would have been able to do in your physics class in school. And the measurements must be made with realistically obtainable equipment, or sensors, and you'll be expected to describe a method in which requested data can be analyzed, either graphically or by comparative analysis. Then the second part, um, you'll be given experimental data collected in order to answer a similar question that's not identical. That and you'll be asked to use the data to create a graph that you can analyze to determine the answer to the question. For example, the slopes or the intercepts of a line can be used to determine a physical quantity, or the nature of the slope could answer the question. The fourth type of question is qualitative or quantitative translation. 8 points. It's worth the least out of the four, but again, not by much. Um, So it assesses your ability to connect to the nature of the scenario, the physical laws that govern the scenario, and the mathematical representations of that scenario. You'll be asked to make and justify a claim about that scenario and derive an equation related to it. And then you'll be asked to do one of these three things. Um, Justify why your answers might or might not agree. Use your representation to make a prediction about another scenario or another situation and justify your prediction. Use your representations to make a prediction about how they would change if properties of the scenario were altered and justify the claim using consistent reason or analysis. And while you might not be directly assessed on your ability to create diagrams, those skills might help you answer the question. So like you might find that drawing a free body diagram is helpful, even if they don't specifically ask to do it for points. But you will earn points for the explanations and the conclusion that the diagram indicates, or maybe the derivation that from the diagram, but not for the diagram itself if it's not asked to. Does anybody have any questions about the exam structure or about any of the individual questions?
Let's see. I'm looking in chat. There are just four answer options.
Yeah, so this year they made it so that all AP exams have just four answer choices, which is nice.
Yeah, there's only one correct answer each. I know for physics one, they used to have the questions where you could have there were like five questions at the end or something that would have two correct answers each for physics one and physics two. Uh, yeah, the estimate for yeah, probably around an hour. I mean, hour or two, but yeah. All right, if we're all good, then we will start the meat, doing the questions. All right, so I'll start us off with this first multiple choice question. So let me just make sure let me just make sure I don't see like request to speak because I think there. Okay, yeah. All right, let's start with this first multiple choice question. So first things first, always. Now, I will say one thing that's going to be tricky this year is the exam is going to be online on Blue Book, so it's going to be harder to mark up the problems as you do them. So, if you want to take advantage of the highlighter tool and just make sure you're reading the questions carefully as usual. All right, so we can choose a different color. Is that a different color pen? No, I don't like that color. Okay, whatever. Oh, okay, let's use a different color. That's why not. All right, so let's take a look at this first one. A block is released from rest.
Lana wants to share some food tips in chat, so we
Oh,
can go over those before we start.
oh, okay. Yeah, yeah, absolutely. Okay,
Okay.
okay. Sounds good. All right, so yeah. So yeah, do pay attention to chat because we're gonna have some Blue Book tips, which is gonna be really nice because Blue Book is the new software that I believe 20 about I think 28 of the AP tests are using this year because a bunch of them are going online this year or at least hybrid.
Yeah, almost all of them.
Yeah. Oh yeah, all of them are gonna be on Blue Book except for if they use a CD player or if it's like Chinese or
Yeah,
Japanese.
and for the first physics and some of the other sciences and math,
Mhm.
um, all of the questions and any typing will be online, like any writing, but any like diagrams will have to be answered on paper.
Yeah, it's going to be like the questions will be administered through Blue Book, and then everything else will be written on paper because it'd be a rather pain to do physics on the computer. And I mean, I don't think College Board would bother putting LaTeX software to type in.
Yeah.
Yeah, I saw someone talk about my overleaf tabs. Yeah, I do have multiple overleaf tabs open because I work with LaTeX a lot. It's a good software. Would do recommend LaTeX for math stuff, especially linear algebra. You cannot do matrices in Google Docs, not that I know of. All right,
Uh,
so
yeah. And if you want to use LaTeX in this server, there is a Texit bot.
yes, yeah.
Yeah.
Alrighty, we're getting all the STEM devices today. All right, so let's take a look at this. A block is released from rest and slides down a track with negligible friction, descending a vertical distance of 5 meters from its initial position to point P. All right, so it's going to start from here, go down 5 meters. The block then slides on a horizontal surface where the coefficient of kinetic friction between the block and the horizontal surface is 0.20. How far does the block slide on the horizontal surface before coming to rest? So there's a couple of things that we want to consider in this problem. So what we want to think about first of all is what's happening as this block starts from its initial position and goes down the track. So what does the block have here? It has gravitational potential energy, right? And then once it gets to point P, because there's no friction, no non-conservative forces, we're going to have conservation of mechanical energy all the way from the initial position to point P. So that's a good place to start from. The next thing we're going to think about is what happens once we start from point P and move on the friction, the rough surface. That's what the word is, the rough surface. What's going to happen is we're going to have friction doing negative work and having the kinetic energy gradually be lost until the block comes to rest. So we're gonna do this problem in two parts. We're gonna start by calculating the kinetic energy that the block gains as it slides down. So we're gonna start with conservation of mechanical energy. So K naught plus U naught is equal to K. Let's just call this Kp, which is the kinetic energy at point P plus the potential energy at point P. So we're starting from rest. That means that K naught is equal to 0, and then U naught is going to be equal to mgh. So I'm just write that down. Kp is going to, which is our kinetic energy at point P, is 1/2 mv squared. And then if we're assuming this is y equals 0, relatively speaking, then the potential energy is going to be 0 at that point. We can also think of it as the change in potential energy is equal to the negative change in kinetic energy. We can also think of it that way. That's also where the principle comes from, because you're not losing any energy to non-conservative forces such as friction or air resistance. What we're then going to do is we can cancel out this mass, and for these problems we can assume that gravity is equal to 10. We can approximate it to be 10 meters per second squared. So we're going to plug that in. 10 meters per second squared times the height, which is 5 meters, is going to be equal to the velocity squared times 2. So here we're going to have, on this side, we're going to have 100 meters per meter squared per second squared is equal to the speed at point P. I'll call this VP just for the sake of variables. And then once we take the square root of that, we're going to get that the velocity at point P, or really speed in this case actually, is 10 meters per second. So then what we're going to do is we're going to figure out, we can use a couple of different things. We can use kinematics from here to figure out how far it's going to slide, or we can use conservation of energy again, or we can use not really conservation of energy again, kind of conservation of energy again, to figure out how much work does friction do. So I'm going to show you how to do it first with kinematics, and then I'm also going to roughly explain how to do it with energy. So force of friction is equal to the coefficient of friction times the normal force. So that's going to be equal to, and then force normal here, because the net acceleration in the y direction is 0, is just going to be mg. So let's see if we can figure out the acceleration that comes as a result of the force of friction, and it's going to be negative. And I'm going to put absolute value bars here, but we're going to end up subtracting the force of friction because to put the free body diagram here, when we're sliding along here, the force of friction is going to be acting towards the left, right? So we're going to say the mass of the block is m and acceleration of the block is a. I'm going to set this negative now, mu k mg. You'll notice the m drops out of the equation, so the acceleration is just going to be equal to negative mu k times g. So acceleration is going to be equal to negative 0.2 times 10 meters per second squared, which is going to be equal to negative 2 meters per second squared. So that's going to be our deceleration, essentially. Now we have our velocity initial and we have our acceleration. We can use our kinematic equations to figure out the change in x. So we can use the kinematic equation, v final squared is equal to v naught squared plus 2 acceleration times the delta x. So v final is going to be 0, v naught is going to be 10 squared plus 2 times the acceleration, which is going to be 2, delta x. We do some algebra here. Actually, this should be negative 2. Apologies. 0 is equal to 100 minus 4 delta x. Simple algebra gets us that delta x is equal to 25 meters. So our answer should be D, 25 meters. So that's how you do it with kinematics. That's how you can do it with kinematics. Now, debatably, the easier way you could do this is you could also do it with energy. So you can basically just take the kinetic energy at point P and do work done by friction is equal to 0. So kinetic energy at point P minus the force of friction times delta x equal to 0. You can do the same method, plug numbers in, and you will get that delta x equal to 25 also with this method. I'll put the numbers in just for clarity because I don't want to just leave this hanging like that. So we'll have 1/2 of 1/2. You're going to notice the m's going to drop out the equation again. Force of friction, of course, mu k mg delta x equals 0. You plug in all those numbers, you're going to see that delta x equal to 25 again. So that's how you can do it also with conservation of energy after that. All right, so the answer here is D. All right, let's go on to question 2 now.
Yep. So for this next problem, um, for the velocity as a function of time for an object moving along a straight line is shown in the graph. For which of the following sections of the graph is the acceleration constant and non-zero? So, uh, so acceleration is constant and non-zero. So the acceleration being constant, since we have velocity, um, acceleration is the derivative of velocity. And so if acceleration is constant, then that would mean that velocity is linear. And then for acceleration to be non-zero, that would mean that the velocity is changing. So it's not just a straight horizontal line. So using that, the only times where the velocity graph is linear and also changing are between R and S, and S and T. And so from that, we get that the answer should be choice B, RS and ST only.
Yep, just a simple kinematics. But be that. That is that. All right, question 3. So the net force exerted on an object that moves along a straight line is given by a function of time. F of t is equal to a t squared plus b, where a is equal to 1 newton per second squared and b is equal to 1 newton. What is the change in momentum of the object from t equals 0 to t equals 3? All right, so this is a relatively simple question so long as you know what the change in momentum is. Change in momentum is equal to impulse, and as you may know, change in momentum is also defined by, if you think about impulse, you think about how the force, when you think about, for example, two blocks bumping into each other, that short impulse is just an integral of force over time. If we look at the formula sheet, this isn't, that's not the same scenario, but if we go to the formula sheet, we will see that I'm not sharing my formula sheet screen right now because it's only on one window. But the equation from the formula sheet that tells you this is that the impulse, which is the change in momentum, is equal to the integral of force with respect to time. So change in momentum is equal to the integral of force with respect to time. And in this case, we want to figure out the change in momentum of the object from 0 to 3 seconds. So because we're already in newtons per second squared, we don't need to do any other conversions for that matter. So all we need to do is simply, all we really need to do is plug this straight in, 0 to 3, at squared plus b dt, and then take the integral, relatively simple integral, at to the third, reverse power rule, bt, 3 to 0, plug that in. We're going to get a times 3 cubed, which is 27 over 3 plus 3b, then minus 0, because when you plug in 0 to both these, just becomes 0. So we just get 9a plus 3b, which is equal to 9 times 1 plus 3 times 1, which just gives us 12. So the answer is going to be B. And keep in mind that because P is equal to mv, our units for momentum are going to be uh, kilograms times meters per second. So that's our momentum unit. So that is that question. That's all we got for that question. Oh, hold on. Oh, wait, I just realized I think I accidentally clicked the button. Hold on. Let me go back in. Oh, hold on. Let me reconnect it.
Are you still there?
Yeah, hold on. I think I might have clicked a button on my phone on accident that made me join by my phone. Okay, see if I can.
Okay.
Let's see. I just got pinged. I need to respond to the ping. Let me make sure I'm on my screen right now. Okay, that's question 3. All right, let me just build question 4, and then we can keep going. Respond to the ping I got in chat.
Okay. So question 4. A spherical star spinning at an initial angular velocity omega suddenly collapses to half of its original radius without any loss of mass. Assuming the star has uniform density before and uniform density after the collapse, what is the angular velocity of the star after the collapse? So for this problem is an application of conservation of angular momentum. So the equation for conservation of angular momentum is L equals where's that? I can write it the same way. Um, okay. L equals I omega, where I is the um rotational inertia, the rotational moment of inertia. So the initial angular momentum will equal the final angular momentum before and after the collision. And so the and then we can expand this. Okay. So the initial angular momentum is just W. So I'm just gonna, or I mean just omega. So okay. Um, so now for the moments of inertia, you might not remember the moment of inertia formula for a So for a sphere, for a solid sphere, but it is 2/5 um, is 2/5 mr squared. Um, but if you don't remember that, I'm just gonna call this um a mr squared because it does end up canceling out. Um, and these equations aren't on your reference table, so um, you to know that you would just have to have it memorized. So we have k, and then the mass is the same on both sides, so I'm just going to call that m. So k m r squared, and then times omega. Um, do you know if we need to have any of the rotate any of the moments of inertia memorized?
Um, I would find it helpful to
I don't
have
think
usually.
so.
Oh,
But,
I don't think it's a
okay.
requirement, but I feel like it's helpful to have at least a
So
couple common ones memorized.
okay, for this side we have k, and the mass is the same. Now the radius is halved
Yeah.
squared, and so we have this final omega, right? So now that's what we have to solve for, right? The angular velocity after the collapse. Now we have a ton of things canceling. We have this coefficient in front of the moment of inertia canceling, and the mass cancels on both sides. And then if we expand the parentheses on the right side, we have r squared over 4 times the final omega, and then we can divide both sides by r squared, so that also cancels. And then multiply both sides by 4, and we'd get that omega final equals 4 times omega. And so from that, we get answer choice D.
Yep. Alrighty, so angular momentum. Good stuff. Alrighty, let's take a
Um,
look at this.
to derive a lot of these, you need to use multivariable calculus like double or triple integrals. And so you're not expected to derive anything except for like a rod. Yeah, because for a rod, you don't need to use any multivariable calculus. It's
Yeah,
just a single linear variable.
yeah. For sphere, I think you can also do it. It's just that you have to change the differential element. So like, I remember this was actually on last year's AP test. I think we had to derive it for a sphere, but
Okay.
for non-uniform density. But it was
Any
like,
questions with any of the questions that we've done so far?
let's check. Any questions so far? Ready? Yeah, I mean usually it's just
Okay.
round spheres, but yeah.
Move on to the next question then.
Yep. Alright. So all right. This was one of those ones that they throw you a lot of information at, but it's really just a matter of simple dependencies. So let's take a look. Pendulum is constructed by attaching a 1 kilogram sphere to the end of a light string that's fixed to a ceiling. Let's label that 1 kilogram. The second 1 kilogram sphere is attached to the end of a spring, which is also fixed to the ceiling. The pendulum and spring have the same length when in equilibrium as shown in the figure. So same length at equilibrium. Both spheres are displaced from equilibrium in the directions shown and oscillate with the same period. If the 1 kilogram spheres are replaced with 2 kilogram spheres and the amplitudes of oscillations are unchanged, which of the following is true about each of the resulting periods of oscillation? So we're being asked about periods of oscillation. So all we really need to do is take a look at the two equations for the periods of simple harmonic oscillators. So we don't need to know any differential equations or anything like that. We just need to look at the equations on the formula sheet regarding the oscillation periods for these two things. So for a pendulum, the period of oscillation is equal to 2 pi root L over G, where L is the length of the pendulum and G is the constant of gravity. And then for a spring with a mass attached to it in any given orientation, the orientation doesn't matter. If you use the differential equation, derive it, you're going to see this is true. or Newton's laws really to derive that, you're going to see that the period of a spring, of a mass on a spring, is 2 pi root m over k. So what we're changing, the only thing we're changing in both these scenarios is the mass of the spring. So if we, oh sorry, the mass sphere is what I meant. Sorry about that. But let's take a look at the period of the pendulum. So our question is going to be, what is the dependency between the period and the mass for each one of these? So if we look at the equation for the period of a pendulum, we're going to notice that there is no dependency between the period of the pendulum and the mass of the object. So we can conclude that the period of the pendulum won't change if we change the mass, because the period of the pendulum is only dependent on the length of the pendulum. Whereas for the spring, on the other hand, the spring, we do have a dependency based on mass. And what we notice is that the period of the pendulum is directly proportional to the mass. So that means that if we increase the mass of the sphere, the period of the spring is going to go up. That would make sense because that would make sense intuitively, because the more mass you have in a spring, the more it's going to be harder to move because there's more inertia, and thus it would take longer for the spring with the greater mass attached to complete one full period of oscillation. So we can conclude that for the pendulum, it remains the same. So let's cross out C and D. And then for the spring, increases. So we get that our answer is B. That is just simple harmonic oscillators. All right. All right, Pernille, are you talking? I don't think I can hear you. Is it just me, or is
Oh,
it just
okay.
me? Okay, I can hear you now.
Can
Okay.
you hear me now? Yeah, okay. Okay, so question 6. A heavy sign of mass M is held at rest by two supporting wires between two buildings, with each wire making an angle theta with the vertical, as shown in this figure. What is the tension in each wire? So we can start this by drawing a free body diagram. So we have this mass M, and so down we have the force of gravity, and then we have these two tension forces, and we know that they have to be equal to each other, um, because it's the same angle, and they're just identical, they're symmetrical. So those two tension forces are equal to each other. Um, and so now we have to, so held at rest means that the net force on the mass is 0. So sum of forces is 0. Um, and so we can break that down into having the sum of forces in the x direction, and the sum of forces in the y direction each equaling 0. So for the forces in the x direction, we have the horizontal components of the two tension functions, or I mean forces. Um, so for those horizontal components, so we have this angle theta and theta. And so those horizontal components, if you use some SOHCAHTOA or whatever, you'll see that they are equal to ft um, sine of theta. Um, for okay, so we can define positive as pointing to the right. So this one is for the right wire, and then for the left wire, it's the same, but it's in the opposite direction. So minus ft sine theta, um, and that equals 0. So we don't have to worry about those because those are already zero. They're the exact same. So they just cancel each other out. Now for the y direction, we have to look at the vertical components. So um, we can define up as positive. So we have um, 2 times ft cosine theta because that is going to be these vertical components of each of the forces. Um, and there's 2 of them. So and then minus because it's down the force of gravity. Um, and now we can, okay, and this has to equal 0. Sorry if this is a bit crowded. Okay, so we have 2 times, or let me do parentheses, 2 ft, the tension force cosine of theta equals the force of gravity, which is just mg, or sorry, capital M. Um, and so now we can just easily isolate ft. So we divide by 2 cosine theta on both sides, and we get that ft equals mg over cosine theta, which, or sorry, over 2 cosine theta, which should give twice b. Any questions? Okay, guess we can move on to question 7.
All right, let's take a look at this next one. All right, so in an experiment, two blocks made of different materials are placed on the same wooden board, which is initially horizontal. The table provides 3 values for each block: the mass, the area, the side of the block in contact with the board, and the coefficient of static friction between the block and the board. One end of the board is slowly raised. Which of the following correctly identifies the block that will start sliding down the board first and includes the appropriate reason? All right, so different materials, initial horizontal. So I always draw a picture just to get a visualization. So we have 2 blocks. We slowly start inclining them. So we have these 3 quantities and all that stuff. Slowly raise the board. So what we're going to want to consider in this context is, let's just, for the scenario, let's draw out a particular moment in time when you have the um, incline and you have the block on here, right? We're in the process of rising this incline. At any given moment in time for the incline, we're going to draw a free body diagram of this. We're always going to have, let's just call the mass of the block M, and then G. That's going to be our incline. And we're also going to have the force of static friction. Force of static friction is going to counteract the horizontal component of gravity along the incline. So force of static friction. So what we're going to look at here, keep in mind that static friction has essentially a limit. Static friction can be can be can change in value depending on how much the incline is inclined. So the maximum static friction is the coefficient of friction times the force normal. When we are not at an incline, we don't have any static friction. We just have gravity and the normal force. Once we start increasing the incline, we're going to have a component of gravity that acts along the incline in the downwards direction. Oh, I forgot the normal force. Silly me. So what we do in scenarios like this is we often define a new set of axes. What we do is we say our direction along the incline to be x and our direction perpendicular or orthogonal to that incline to be y. So what we can do in this scenario is we can do some sums of forces. When does the block begin sliding down? That happens when the horizontal component of gravity, the x component of the gravity, is greater than the static friction. So static friction is going to be mu s times Fn. We're basically trying to figure out when that becomes less than the horizontal component of gravity, which is mg times sine of theta. Sine of theta. So this direction, so if we make a component of that gravity, we're going to have some, we're going to have mg sine theta. That's not part of the free body diagram, that's just the component. We're going to have mg cosine theta acting in the other direction. That's directly opposite of the normal force. Normal force ends up becoming less and less as we the incline the plane. So force normal we're also going to put in terms of mg and theta. That, as we just said, is mg cosine of theta. And the reason for that is because the sum of the forces in the y direction is equal to 0. So force normal minus mg cosine theta is equal to 0. That was a terrible handwriting. Okay, what's wrong with my handwriting? It's equal to 0. Force normal is equal to mg cosine theta. If we write out this inequality again, we're going to see that our mg cancels out, and that the question we have tried to ask is, when does the block begin to slide? It begins to happen when this equality becomes true. So when tangent of theta is greater than mu sub s. So when we get to this threshold is purely dependent on the coefficient of friction. So there's no dependency. So this is essentially useless. There's no dependency on area and there's no dependency on mass. So these two columns are essentially just extraneous information that we don't need to consider. So which one we're essentially trying to ask, because tangent of theta, the greater theta is, the greater tangent of theta is going to be. So that's our relationship that we will establish. So here we're trying to figure out which one's going to slide down the board first. And that is going to be the object that has less that has less has a lower threshold for friction. The lower threshold for friction is going to belong to the object that has the lower coefficient of friction, which in this case is block 1. It has a coefficient of static friction of 0.20. So in this case, we're going to have our answer be B. Block 1 is going to start sliding first because the coefficient of static friction is smaller. And what that means is that there, as I was just explaining back to here, there is a lower threshold that the x component of gravity needs to overcome to get a net force in the direction along the incline to bring the block in the downwards direction, essentially. So that is how we got the answer of B. Any questions on that one? Silly novel operator guy. The last part, yeah. So essentially, like, you mean like how we got the conclusion part of it, like the mu s, or essentially what happens in this last part is we figure out we figured out the dependency we figured out the dependency the between the theta required for that's required for the block to begin sliding downwards. So the block begins sliding downwards when tangent of theta is greater than mu s. So the block that will start sliding down first will be the one that has the lower threshold, that has the lower theta threshold. So what this means is that the lower mu s is, the lower theta will be. So the lower mu s is, the lower theta will be, and the earlier the block will slide down. This inequality right here is basically telling us the threshold is telling us the minimum value for theta for which the gravity will begin doing work and causing the block to slide downwards. So the oh no, the so the lower threshold is corresponding to a lower coefficient of friction, not a higher coefficient of friction. Because the lower the coefficient of static friction is, the easier it is. So think of it. I guess another way you can think of it is ignoring the math perspective of it, thinking of it from the physics intuition perspective of it. If we think about if we think about coefficient of static friction, the higher the coefficient of static friction is, the harder it is to get an object to start sliding. So if you have a lower coefficient of static friction, that means it's going to be easier to overcome that threshold to get the block to start sliding. Therefore, for the block with the lower coefficient of static friction, you don't need to incline it as much for the gravity to start doing work to accelerate it down the incline. Does that make more sense? Okay, that's good. Yeah, sometimes it's also thinking about it from like the physics intuition kind of perspective also helps. So uh, that's also something that uh, is helpful. Yes, if the incline, so before we get to that threshold, the greater the incline gets, the more static friction there is because as you increase the incline, what happens is the higher the incline is, the higher the incline is, the more gravity, the greater the component of gravity parallel to the incline is acting. So that means you have more static friction going in the opposite direction because static friction, it's not always one singular value. You can have no static friction in this horizontal scenario right here. You might have no static friction because there's no gravity in the horizontal direction. But then once you start inclining it, static friction becomes greater and greater so that the net force in the x direction consistently stays at zero. It's once that threshold is overcome that you get a net force in the positive x direction. Yeah, static friction is a reactionary force. It's dependent. Yeah, this goes back to Newton's third law. Yeah. Yep, equal and opposite forces, Newton's third law. All right, any other questions on this question? You technically could have. You technically could have. You could have just thought about it as, but I think it's helpful to I think you could have done it without the math and with intuition, and you could have guessed and got the right answer. However, yes, it's not always the best way to go about things, especially when you're dealing with scenarios where you're not always certain about the dependencies between variables. Because one of the biggest things that you're going to see in physics, and this is something that I'm really going a lot through because I'm self-studying the electromagnetism exam this year. And one of the biggest things you're going to realize with physics is that examining functional dependency is critical when you're analyzing scenarios because with what the math gets you is it explicitly tells you what is dependent on what. Because for example, if we go back to question number 5 about the dependency between mass of the sphere and the period, writing out the equations, what that gets you is it tells you the functional dependency between the period and whether it's mass or length. What we learn from that is that for the period of a pendulum, where we don't have a dependency on mass, but for the period of a spring, we do have a dependency on mass. So what the math is going to get you, yes, it will never fail you. That is very true. Math, the critical part about math is it will get you the functional dependency. I know I'm repeating that word a lot, functional dependency, but that is what's critical about the math aspect of physics. So intuition, if you're stuck low on time and you need to guess an answer, intuition could might as well get you that 1 point. But if you have the time to do the math, do it. Yeah, self-studying E&M, I'm gonna say it's pretty tough, but you will, if you have a solid understanding of mechanics and like you put the time into it. I'd say the big thing is you want to put time into it. Oh, we're all in the same boat. This is this is so funny. Yeah, I mean, so far I'm finding that the more time you spend on topics, the better. Yeah, well, we're all on that boat, same boat. So yeah, yes, yes, I can definitely post the PDF at the end of the session. Yes. Oh boy, we're all. So, AP Classroom's a big one. Flipping physics, all that good stuff. Crack AP too has a lot of good questions, and then just stuff online in general is pretty good. All right, you want to keep going on though? I don't want to dwell on too long, but yeah, it's yeah, electricity and magnetism. All right, let's do question 8 before we get too sidetracked. Hey, Pernille, are you speaking? I don't think I can hear you.
Oh, sorry. Okay.
You're good. You're good. Good.
Um, a student lifts a ball straight upwards at a constant speed. The energy bar diagrams represent the gravitational potential energy UG of the ball Earth system and the kinetic energy K of the ball at a time t equals t naught and at a later time t equals t final. Which of the following energy bar diagrams correctly represent the change in mechanical energy delta E of the ball Earth system for the time interval delta t equals t final minus t naught? So conservation of mechanical energy. So the total mechanical energy is equal um, to the gravitational potential energy plus the kinetic energy of the ball. And so we can kind of just like count units. So here we have one, and then here we have one, two, three, four. And so the change is 3 units of energy. And so with that, we can get twice the where we have a change of 3 units of energy. Any questions with that?
Seems like we're good. This one seems relatively simple. All right. All right. Let's take a look at number 9. All right, 9. So, uniform beam of length 0.60 and mass 4 kilograms is connected to a wall by a pivot. The beam is held horizontally by a string fixed to the beam and the wall. A block of mass 1 kilogram is then attached to the end of the beam. I'm just going to label all these first, but just so let's label as we go on. Let's take a look at good testing habits. So, 1 kilogram block is attached to the end of the beam as shown. Which of the following is nearest to the magnitude of the torque about the pivot exerted by the weight of the block? So, torque is equal to R cross F, which is equal to RF sine of theta. For a review, when we have an axle like this, right, the theta refers to the angle that's between the lever arm as well as the radius. So if you do the right hand rule here, point your I can't, yeah, I don't think I can, I don't know if I can turn on my camera right now, but you point your index finger in the direction of F, you point your middle finger in the direction, sorry, you point your index finger in the direction of R, you point your middle finger in the direction of F, you're going to see that your thumb is going to be pointing upwards, and that is going to imply a positive torque. Now, if you flip that, it becomes a negative torque. Keep in mind that most of the times that we define positive angular displacement in the counterclockwise direction and negative angular displacement in the clockwise direction. Seems a little counterintuitive, but it goes by the unit circle, so it's good enough. Keep in mind that physics things are absolute, but convention is convention, and convention is just an annoyance that we deal with, but it's whatever. So in this problem, there seems to be a lot of information that we need, but also maybe information that we don't maybe necessarily need, maybe not. But what's going to be important here is that we are completely horizontal. So we draw a free body diagram, and what the important thing here is to understand is when you're drawing free body diagrams, you are drawing them assuming that things are particles. But once we get to rotation, we have to consider the significance of rigid body physics. And what that means is you have to consider force acting at a point rather than just on a particle. So in this case, we have this beam right here. The beam, what's going on with this beam is we're going to have gravity acting at the center of mass of the beam, which is right here. And I'm going to put an X here to represent the axis of rotation, and then I'm going to put this dot right here to represent the um, mass of the beam, or the gravity, where this is the gravitational force that's exerted on the beam. We're also going to have the mass of the block exerted at this endpoint right here. And then we have this force exerted by the string to keep this entire system at rotational equilibrium. So in this question, all we're being asked is the magnitude of the torque about the pivot exerted by the weight of the block. So all we really need to know here is the force exerted by the block and its angle relative to our lever arm. So because we're completely horizontal, this this R right here is horizontal, and the F is vertical. So R and F are orthogonal to each other. What that means is sine theta is just going to be 1. So the magnitude of the torque is just going to be equal to R times F. Because sine theta, in this case, is just going to be equal to 1, because this R, F, they are orthogonal to each other, 90 degrees. So R, our lever arm, is 0.60 meters. And then our mass times our gravity is the force. So this is going to be mg, which is going to be 1 kilogram times the gravitational constant. So that is going to get us, what's it going to get us? That's going to get us 6. The answer for that is going to be 6 Newton meters. And that is the answer. That is how much torque that's the amount of the torque being exerted by that block. All right, any questions on this one? So it's a relatively simple torque question, just had to make sure you know how the system works. S2. Oh, the newtons. So kilogram meters per second squared is equal to 1 Newton. Because F equals ma. That's the definition of a Newton. It's a kilogram meter per second squared. Yeah. Yep. All right. Go on to question 10 then.
Question 10. Two blocks of mass M1 and M2 are connected by a thin string that passes over a circular wheel of mass M as shown. The wheel is attached to a vertical stand and rotates freely about its center. The spring does not slip on the wheel and exerts forces T1 and T2 on the blocks. When the wheel is released from rest in the position shown, it undergoes an angular acceleration and rotates clockwise. So when it's released, it starts rotating this way. Um, so which of the following statements about the magnitudes of T1 and T2 is correct? So for this one, for the wheel to start accelerating, or for the masses to start accelerating, there has to be an unbalanced force on the string. And so this tension force um, on the string would have to be greater than this for it to accelerate in this direction. And so using that, um, so yeah, so the T2 has to be greater than T1 for it to accelerate in this direction, because you need an unbalanced force for that to happen, and we want it to rotate towards T2. So with that, we get choice B.
Alrighty. Any questions on this one? Alrighty. Some typing.
We can draw free body diagrams for the masses. So for M2, we have the force of tension that's trying to pull it up, and then the gravity that's trying to pull it down. Um, and then for M1, we have the gravity trying to pull it down, and then the tension trying to pull it up. Um, so if you were just looking at the masses, um, then um, the gravity here um, would have to be bigger than this, right? Um, but the tensions, so for this to accelerate, the net force would have to be in this direction. And the tension on the string, um, so the whole system is accelerating. So the string experiences an acceleration. And so there has to be a force acting on the string itself. And so that force is the tension that causes it to accelerate. Any other questions?
Alright, I think we can keep going. Alrighty, number 11. So, two small identical blocks, block 1 and block 2, are dropped from rest at different heights above a horizontal floor. So let's draw the horizontal floor now. Draw the horizontal floor right here. I'm just going to draw that. Block 1 has speed v1 immediately before hitting the floor, and block 2 has speed v2 immediately before hitting the floor. Work done by gravity on block 1 as it falls is W1. What is the work done by gravity on block 2 as it falls? So we know that they're both starting from rest, and what we can do is let's do a little diagram here. Right here, we have block 1, V1. V2 is going to be, sorry, not V2, 2V1. That's what I meant to write. 2v1, we're hitting the ground for block 2. So we don't know from how far up they're being dropped. What we do know, however, is that there's no air resistance, obviously, that gravity converted all the gravitational potential energy each of these blocks initially had to kinetic energy. So for block 1, what we know is that, and what we're going to do is we're going to let m equal the mass of each of these blocks because they're both the same. If we had different masses, then we would have to account for that. But kinetic energy final for the first block is equal to 1/2 mv1 squared. Whereas for the second block, it's equal to 1/2 m2v1 squared. So that's going to be 4v1 squared. So the change in kinetic energy for the first block is equal to 1/2 mv1 squared. And the change in kinetic energy for the second block is equal to 2 mv1 squared. So what that means is, and because the change in kinetic energy is equal to the work done on the block, because we start from 0, just so you know that, we start from 0, drop and rest, that means k naught for both of the blocks is 0. The work energy theorem tells us that the change in kinetic energy is equal to the work done on an object. So work done on the first block is equal to 1/2 mv1 squared. Work done on the second block is equal to 2 mv1 squared. If we divide these, we're going to see that W1 or W2 over W1 is equal to 2 mv1 squared over 1/2 mv1 squared. And that's going to get us, if we cancel that out, 2 over 1/2, which is equal to 4. So W2 is equal to 4W1. So with that, we get answer choice D. That's right. All right, that's answer choice D. All right, so to sum it all up, kinetic energy, find kinetic energy, work energy theorem, work backwards, derive. Any questions on that one? I think this one is a relatively simple one. Let me refresh my chat. I'm looking at the chat on my telephone, but so it's okay. 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 We'll move on to question 12 then.
So question 12. A block is hung vertically from an ideal spring. The block is pulled down, released, and allowed to oscillate. The vertical position y of the block as a function of time t is shown in the graph. Which of the following graphs best represents the corresponding acceleration a of the block as a function of time? So on the reference table, we have this equation of x equals x max uh, cosine of omega t plus phi, where phi is um um like horizontal offset on the graph basically, or like some initial position of the object if you want to think about it physically. Um so for here we have y, so we can just switch out the x's for y's in this formula. This is a different variable. Um so oops, okay. And so we can, so this y is the function of time, so I can write this as y of t. Um, Now, the acceleration is going to be the second derivative of the position. So we can just work this through and take the second derivative. So for this, we have the chain rule. So the y-max just stays in the front. We don't really have to worry about that. With our calculations since it's just a constant. So now for here, the derivative of cosine is sine. So and then whatever's inside, and then with the chain rule, we have to multiply that by the derivative of the inside part. So the derivative of this inside part, with respect to time, c is a constant, so that'll just disappear, and so we just get omega, or yeah, um, we just get omega, um, okay, and then the second derivative, um, oh wait, sorry, derivative of cosine is negative sine, so uh, second.
Oh, wait, where'd it go?
Oh,
Ah,
okay. Sorry.
I got you.
Okay, so this times the negative sign of this. Okay. And now we take the derivative again. So again, the y max just stays in front. And then this omega that we have out here is also constant. And let me put the negative in the front to make this easier. Okay, so the negative is in the front, the y max is in the front, and this omega. And then now, so we're taking the derivative of this part, since this is the non-constant part, this part is a function of time. So the derivative of sine is cosine. So cosine of omega t plus t. And then the derivative of the inside function is again just omega. And so we can also rewrite that as an omega squared over here. And so now if we look at this compared to the original function, um, sorry, I'm having some difficulties with my phone. Um, okay, so if we look at that compared to the initial function, the acceleration, then we can see that if we ignore the constant part in the front, um, it's just the negative of the position function y. Um, yeah, the y max and the y min are the same thing. Okay, so we just see that it's the negative of the original y times some other constant. And since we have no units in the y or in the vertical axis, we don't have to worry about those constants. So we just pick the option that is this exact function, but reflected across the x-axis. And so that should give choice A.
All right, any questions on this one? All right. So the y max and min would be different, but the graph doesn't tell us that.
Yeah, so we draw the graph with the equilibrium point at 0, and so the maximum and the minimum oscillation will just be the same. Yeah, same absolute value. Okay.
All
If
right,
there are no other questions, then we can move on.
question 13. All right, here we are at the point of gravitation. So gravitation and escape velocity. So a small rock is launched from the surface of a planet with no atmosphere. The initial speed of the rock is 2v escape velocity, where v escape is the escape speed of the planet. What is the speed of the rock when it's very far from the surface of the planet? So first things first, we want to determine what escape velocity is in terms of a couple of variables and constants, because that's going to help us further down the problem. conceptually speaking, I was looking at this problem earlier. I had to do a little refresher from flipping physics. Uh, they had an explanation on that I found very nice. So escape velocity, what that is essentially is the velocity that an object needs to travel at to essentially escape the gravitational pull of the planet, so that initially, so that eventually in the very long term, once it travels very far away from the planet, the gravitational potential energy is going to go down to zero, and the kinetic energy is also going to go down to zero. Because remember that with conservation of mechanical energy, with no non-conservative forces, we have delta k plus delta u is equal to zero. Keep in mind that the gravitational potential energy is measured because of the way it's measured. It's just a matter of convention. It is negative. You can also derive it from the equation F is equals negative du dx. But gravitational potential energy is given by the equation U is equal to negative gmm over r, where m, uppercase and lowercase, represent the two objects in question. And U represents the gravitational potential energy of the system of the two objects. It's a good time to bring in mind that remember that potential energy does not belong to objects themselves, they belong to systems of objects. Kinetic energy can belong to objects, but potential energy always belongs to a system. That's why in questions of you'll see the verbiage of questions saying consider the gravitation or consider the potential energy of the Earth block system, for example, because the gravitational potential energy is being stored in that basically little distance between the Earth and the block, not just the block itself. The the potential energy gets converted to kinetic energy. Potential energy gets converted to kinetic energy. So as we move very far away from the planet, this u is going to increase. That means the k is going to decrease. So what escape velocity is going to be defined as is we're going to have our initial 1/2 m v escape squared. That's going to be our initial plus our initial, going back to the k naught plus, actually no, wait, sorry, I should be using this equation. Our final kinetic energy is going to be 0 minus that, and our initial gravitational potential energy is going to be, wait, what? I might be doing this wrong. Final minus initial, final 0 minus initial. Wait, hold on, I'm doing something wrong here. No, never mind. Okay. 0 minus negative gmm over r. So that's going to end up just being 0 plus gmm over r is equal to 0. So we can derive an expression for the escape velocity in terms of the mass of the planet and the radius of the planet. So keep in mind that r in this case is the radius of the planet because we're assuming we're starting from the surface. So r in this case is the radius of the planet. R in general represents the distance between, the distance between the center of masses of the two objects. Keep that in mind. So 1/2 m v escape squared is equal to g m over r. Cancel out these m's. Yeah. Oh, after question 14. Okay. Yeah, no worries. Yeah, no worries. Yeah, I can take over for some of the first response, or we can, yeah, I can brush through the first response so we don't, because the session is it's getting that 2 hour mark. So yeah. So v escape squared is going to be equal to 2gm over r. Take the square root of that. Oh, then we can get rid of that squared right there. So v escape is equal to 2gm over r. So what's going to happen here is we're now going to consider our scenario where we're launching it with double the double the escape velocity. So we're going to have our delta k. Our delta k is going to be our kinetic final kinetic energy minus our kinetic energy initial kinetic energy. Our final kinetic energy is what we're trying to figure out. So we're going to just say that is we're trying to figure out what the speed is when we're very far away. So we're going to have 1/2 m v final squared minus 1/2 m times 2 v escape velocity squared. So that's going to be 4 v escape squared plus the change in gravitational potential energy. At the final position, it's going to be 0, and at our initial position, it's going to be gm over gm m over r. That's going to be equal to 0. So all we're really doing now is we're just solving for all of this. 1/2, and we're going to, before I keep going, I'm going to, first of all, just drop all of these m's out of the equation. 1/2 v final squared minus 1 minus 2, that is now 2 times v escape velocity squared, which is going to be just going to be 2 gmr. If we get rid of that, plus gm over r is equal to 0. Now we're going to just do some simple algebra here. 1/2 vf squared minus 3 gm over r is equal to 0. And then v final is equal to 6 gm over r. And then we just take the square root of that. And we see this in terms of our initial escape velocity. V escape times root 3 is equal to a velocity final, because this is root 2 and this is root 6. That's our v final. So our answer is going to be D. So it's a lot going on here, but but a big part of this is just knowing about what escape velocity means. So that's an important aspect of this question. From there on out, it really just is a conservation of mechanical energy, because there's no air resistance and there's no friction, obviously. All right. I think we can go on to. All right, let's go on to question 14 then.
Okay. So question 14, two uniform disks, A and B, each of mass m, have radii 2r and r respectively. The rotational inertia of a uniform disk of mass m and radius r is 1/2 mr squared. Disk A rotates in a horizontal plane about its center with angular velocity omega naught, and disk B is initially held at rest. Disk B is then released and falls onto the center of disk A, such that both disks spin together about their centers without slipping. What is the angular velocity omega final of the two disk system? So this problem is conservation of angular momentum. So again, our formula for angular momentum is L equals I omega. And so our initial will have to equal our final. So initially, disk A is moving and disk B is stationary. So um, I A times 0 radius per second plus uh, I B. Oh, sorry, I switched that around. Okay, plus I A times omega omega naught. So this is just 0, and then on the final side, we have their combined moments of inertia, and then they're moving at a final velocity together. So now we have to plug in the moments of inertia, and they give us this formula up here. R is 1/2 mr squared, or sorry, not R is the moments of inertia. Okay, the rotational of inertia of a uniform disk of mass is 1/2 mr squared. So our formula is I equals 1/2 mr squared. And both objects have the same mass. So we have um, sorry, I keep clicking something and then it makes me not be able to edit. So let me fix this really quick. Okay. So we plug in for the moment of inertia of A. So we have, oh, why is it doing that? Okay. So we have, why is it not writing? Okay. Sorry, my phone is being annoying.
Uh, yeah, phones are
Um,
always wacky.
if this doesn't work, I'm just gonna try writing on my computer. But okay, it's working now. Okay, sorry about that. Okay, so the moment of inertia of A is 1/2, and then our m is the same m, and then its um, radius is given as 2r, and then all this times omega, and then this is squared, um, equals, and then add our two moments of inertia together. So for the first one, we have 1/2 times m times 2r squared plus 1/2 times m times r squared, and then all of that times omega final. We have all these 1/2s. We can just cancel them out to slightly simplify our arithmetic. So now on this side, we have 4m r squared omega minus omega naught equals, and then in here we have, this is going to be 4 from the 2 squared, and then plus the 1. So we're going to get 5 times mr squared times omega final, and then r and m cancel, r squared and m cancel, and so we are left with omega final equals 4/5 of omega naught. Um, and so that should give choice B. Any questions with that one?
I just see a message get sent and get deleted very quickly. Go ahead.
Yeah,
Okay.
that was Autobot taking action. Um,
Yeah. All right.
okay. If there's no questions, then I'm going to go now.
Okay.
And we can move on to the next question.
All right. I'll take over from here. All right. Thanks so much, Manil.
Yep, thank you.
If anyone wants to volunteer to come on stage and co-host, I mean, we can. I mean, we are getting to that 2 hour mark, so we can begin to wrap up the session soon. But I do want to at least touch on the response a little bit. So, what I'm going to do is I'm going to let's finish up question 15 first, and then to wrap up the multiple choice, and then we can. I mean, we're getting to that 2 hour mark, so I don't want this to go on for too long, so we're not all super tired by the end of the day. But let's finish the task at hand. Okay, so remember this question. So a massive truck MT is initially at rest with a load of sand and initial mass MS. At time t0, the truck is pushed forward by constant force F naught, and the sand begins to leave the truck as shown. Mass of sand that is left the truck as a function of time is given by CT, where C is a positive constant with appropriate units. Hypothetically, you could have a multiple choice question that asks you for, what units are, I've seen those questions before on AP Classroom for sure. You might be asked for like units of stuff, but anyways. At time t1, there's no sand left in the truck. Which of the following graphs most nearly shows the velocity vt as a function of time? So this question has essentially two parts to it. We need to figure out the change in velocity with respect to time before the mass before the mass stops changing and after the mass stops changing. So with this question, it seems a little bit daunting to approach at first. So what I like to do with these types of questions is we do a little bit of process elimination. So one thing that we're going to note is that let's start, I think an easier point to start with for this question is what happens after the mass stops changing. So F equals ma. When force is constant, and mass is constant, when F is not changing and m is not changing, that means A is also A is also not changing. So what that means is that A is a constant as well. A is equal to dv dt. So essentially, after t, when t is greater than t1, what that means is the slope of v is a constant. So so what that means is v is linear. Where is v linear? Well, one thing that's important to note is that the velocity the velocity is going to keep increasing because f naught is not zero. We know that for sure. So we can't we cannot say the answer is B because the velocity is going to keep increasing. It's not D because VT is not linear here. So now we're left between A and C. So here is where we're going to do the bit more tricky reasoning. Now, you could, like an earlier question, go by intuition and do that kind of stuff. But what we're going to do is we're going to do a little bit of deriving differential equation work right here. So let's go back to our equation F equals ma. F naught is equal to m times A, which is equal to m times dv dt. So force is constant. Mass is not constant. Mass can be expressed as a functional dependency of time. So we have initially the mass of the truck plus the mass of the sand, and we're going to subtract ct. That's our mass. So what this means is if we want to find a function for velocity in terms of time, we have this differential equation set up here. Now, we're not going to solve it because that's pointless for this type of question. But but with our knowledge of differential equations, we know that if we integrate both sides here, this is not going to be linear. V is not going to be linear in terms of t. I think we can pretty easily tell that based on this differential equation that we've derived. So that hints us to the fact that answer is not A, and we can eliminate that one too. And the answer is C instead. You would not be expected to solve this differential equation. However, the key takeaway with this part of the solution is that you're able to set up a differential equation and understand what's changing and what's not. So force naught is not changing. F naught is a constant force that's being applied the same for all the times. And then your mass is changing in terms of time, with respect to time. So you're going to get something like something ln, something whatever. It's going to look somewhat logarithmic. It's going to be like some logarithmic exponent. It's going to be exponential, is what it is going to be. That's what it's going to be, I believe. But oh wait, no, it's actually yeah, it'll be no, it's going to be logarithmic because this side's going to become b. But whatever the case, it's safe to conclude that it's not linear. That's the key takeaway from that part of the question. So with that, force, if you think about it, if you check it with intuition, you'll realize, okay, I'm pulling this along. As time goes on, it gets easier and easier to change the velocity. So the velocity increases faster, and then once I get to a certain point, it's the same level of easiness to change the velocity of the mass. I'm just gonna move this up a little bit. because when the thing gets printed, when I send out the printed version of it, it's going to be easier to just move that up. Okay, so that is the multiple choice. So just to skim through the multiple choice over one more time, we've covered pretty much all the ground we have with multiple choice. There's some questions I'll ask you to actually do calculations, some more conceptual questions to see graphs, some simple calculus questions. All around, there's definitely less an emphasis on tedious computations and more so the conceptual analysis because you see that there's not that many decimals. It's really just all a bunch of numbers and there's a lot of graphs. So multiple choice really is about it's really that full mix of everything. And strategy with multiple choice always do the easiest questions first. That's it. Always do the easiest questions first because that way you'll accumulate the most number of points when your mind is still fresh and leave a little bit more time towards the end for those trickier questions that require more conceptual thought. And remember, 2 minutes per question. While this is much more time than last year, 2 minutes per question is still not that much time if you think about it. So there's 40 questions, so it's a pretty good amount of questions to do. But 80 minutes is a much more free space of time than compared to 45 minutes, an hour 20. So keep that in mind. Work through the questions one at a time, skip if you have to, and all in all, make sure you're applying conceptual physics, write stuff out. Don't be afraid to write stuff out because the more you write it out, the clearer it's going to be and the less likely you are going to be to make a mistake. So that's the key takeaways with the multiple choice. So do we have any questions on the multiple choice? All good? Alrighty. All right, we're getting to that 2 hour mark. I don't want to completely neglect through the free response. I want to at least maybe take a skim through just at least what the questions look like. I don't think at this point, I don't think there's a. Oh, um, I don't think I can hear you. I don't think I can hear you. That's what it's like. I'm thinking, just so we don't drag out for too long, we can skim through the free response questions, just take a look at what they each look like, and then this will probably take another hour to go through all these free response questions in detail. But um, I'll start with just porting the questions. I'll start with just porting I'm on the wrong screen. Just porting the questions in. So let's take a look. I need to port in 10 pages of material.
Okay. Yeah.
Oh, I can hear you now. Nice. Nice. I can hear you now.
Okay. It's fine if you want to go over collect the long answer questions. It's really up to here me. If everyone else doesn't mind,
Okay.
but again, it's really just
Oh, wait, hold on. You're like cutting in and out a little bit, I think. Yeah, I'm also sensing the audio is a little bit choppy.
is that better?
I think so. Yeah.
Per chance. Perfect. Okay.
All right.
You didn't hear me? It's totally up to you what you want to do. It's fine if it goes a little over.
Okay. So, I mean, there's no like limit per se, like how long it can run?
I mean, definitely not like 3 hours, but if
Yeah.
you're gonna do one and then you're gonna do a second, I think it's better to do two.
Okay.
Um, I don't mind if you don't mind. I don't think this is recorded, but all the screenshots for the answers and the solving will be, I think, available afterwards.
Yeah, I can make all these available. I mean, these are from College Board directly, so like the session's mainly like the purpose of it going into detail, just like
Yeah,
doing the verbal aspect of it. Then I can post
perfect.
that. I can post everything. The recording will be yeah. I have the screen recording on right now. So yeah. All right, yeah. So three, four, all right, all right. Let me just paste these in just so we have the full PDF of it available to us. All right. So as I'm pasting this in, I'll do a little just explanation about what each of these free response questions. I mean, well, we had that earlier as well, but let's go through just a little bit of what the expectations are on the free response. So free response, the couple strategies I'd say. First of all, read the questions very carefully. What AP Physics loves to do, and with a lot of subjects, what the College Board loves doing is they will put a bombardment paragraph of text on the page and expect a full understanding of it. There will definitely be those times when you'll see a whole paragraph of text just get bombarded on the page and it'll just be a whole block. Like if you look at, just as an example, if we go to 2021, actually, no, I'm gonna,
When the College Board does that, I find that it's, like, much easier, especially if you're just doing math, that you just
yeah,
find the numbers, highlight them, so then you could figure out what you're trying to solve for the problem.
yeah, exactly. Because what's happening here is you'll have let's go set one, let's go set one. What they love doing is they'll bombard you with a whole text, a whole paragraph of text right here, and all that's really happening is you have a couple things that are to correspond to a diagram right here, and you're just going to get that. It's a lot of corresponding the words to the picture is what a lot of this text is for. So that's something that you want to be prepared for. Highlighter tool is critical. Highlighting what's going on is critical. All right, so let's take a look at these free response questions right here. So the first type of free response question that's going on, just make sure there's no questions. There's a little yeah, those are definitely three things. I mean, it's also about the kinematics aspect of it, kinematics, dynamics, and all that aspect of it. But those are three very important things in terms of the latter half of the semester generally. But those things will build on things like kinematics and all that stuff, force, kinematics, energy, stuff. And yeah, calculus is going to be critical as well. Okay, so I'm going to take probably like 10 to 15 more minutes just to go through all these questions, just to show you what they look like and what the rough expectation of the approach is going to be. So first question is going to be mathematical routine. So slapping the paragraph here, this sort of looking at the fact that we have F and we have U, we can kind of anticipate we're probably going to have to, no, I need to change the pen tool. We can probably anticipate that we are going to have the equation here that we're going to need to, where's my pen tool? Of course, I can't find it right when I need it. Of course, I can't find the pen tool right when I need it. It's kind of a little bit funny. Okay, why can I not find the pen tool right when I need it? Hold on. Edit. Of course I can't. Let me see what happens if I. Oh, come on, where's the pen tool? That's really annoying that I cannot find the pen tool right when I need it. Uh, pen. The heck's happening? I had the pen tool just 5 minutes ago. What the heck's happening? Am I that technologically incompetent? I thought I was old. I didn't think I was that old.
Sorry.
I thought I was old, but I
Physics ages you.
yeah. Unfortunately, it does. Uh, math is also very aging. Sitting in front of the computer all day. Where's all that stuff? Okay. I don't know what happened to the pen tool. How does I refresh the page? Curiosity.
Oh my god, Gekka's here. Hi, Gekka.
Here's the pen tool. So. Okay, so section 2, free response questions. So mathematical routines. Looking at, as I was talking about before, an anticipated equation you're probably going to have to use is f equals negative du dx. What mathematical routines question is really asking you to do is, in a sense, it's basically a question, do you know how to do math? Do you know how to do calculus? Do you know how to do algebra? Very common type of question, even with the old for response questions, derive an expression, like for example, whatchamacallit, very common type of question, derive an expression for this in terms of that, and that. Very common question type. So in this case, you see, in this case, what we have right here is we have a potential energy graph. We know a force is acting on this object, potential energy, no external forces. This question is really just going to be a matter of conservation of kinetic energy. So derivation, starting with the derivation from the principle, fundamental physics principle, or the reference material, mechanical energy conservation is going to be our best friend here. Yada yada yada. You get the idea. Okay. It's going to sound like a speed run, and that's kind of what it is. But all right, and then why is that so blurry? Of course, it's going to be blurry. Okay. Well, why is that super blurry? That should not be that. Okay. Well, that'll be. All right, well, I'll post. What I'll do is I'll also post a link for where you can find all this in the course and exam description, because this is directly from College Board, so they have the answer, full detailed answer key in there as well. Although they don't have that for the multiple choice, which is good. Which is good that we went over the multiple choice first, so that you have a detailed answer key for that. So this question right here, in addition to being able to write out equations, you also want to be able to graph. So this is where you're going to apply the f is equal to negative du dx equation based on your you're going to want to figure out what your negative slope from this graph is, and you want to graph it on this graph right there. Then another derive this equation kind of thing. You see, you're going to derive an equation for the potential energy. You're going to derive an equation for the potential energy based on a force equation that's given. Integration is going to be what you want to do, essentially. Yeah, you're just going to want to do some integration right here. So that's like the calculus test aspect of it. So integrate that with respect to x, get that, blah, blah, blah. All right, so mathematical routines in a nutshell, do math, do calculus, do the thing. Excuse me. All right, translation between representation. So this one is where you're going to have a lot more diagrams. Again, the big slap the paragraph that College Board loves doing, especially with physics. They don't do that with chemistry a lot. They kind of just give one sentence for chemistry and they just call it a day. But for physics, they love these paragraph slaps. So important thing is to figure out what's going on in this scenario. We have what looks like two identical race cars, each of a certain mass. They're going to make a turn on this road. We have coefficient of static friction is mu. So this looks like it's going to be a centripetal motion question. You're also going to have air resistance, or not air resistance, but air exerting a downward force with this equation. Both cars are going to travel through without slipping. Then car Q is traveling at this speed, and the car S is traveling at this other speed. The air is not moving, so the car's speed relative to the air is the same as the speed relative to the ground. Okay, so yeah, we have that. All right, so then we're going to have this. Then we have our free body diagram. Free body diagram is of course going to be very important. Dot represents, this one represents car Q, this one represents S. The car turns, blah blah. Gravitational force, dot and S dot here, other stuff like that. You can have free body diagram representing that. So that's what the translation between representations means. You're going to have a diagram representation, like a physical representation of what's going on, and also free body diagrams to represent the force components. This page did not get switched. This should be page 23, not 19. There we go. So you might be asked to do things like draw free body diagram, stuff like that, and then again derive an expression. So translation between representations, you might have visual representations, you might have mathematical representations, and the more important part is, and also graphing. That's something we're also going to have, and then more importantly, using all these representations to make either qualitative and or quantitative justifications for certain quantities. So based on the graph that you have, the equations that you got, and the diagram, justify something about the scenario. I'm not going to go into super granular detail about it, but being able to, for example, relate velocity to position, velocity to radius, velocity, and like time, the time it takes to all that stuff. Again, going back to that whole idea of functional dependencies, that's very important here. I know I'm talking a lot about like the big ideas here, but that's kind of that's also important because we're at this point in the course, it's going to be much less useful to go through minutia than just to go through the big details of the course. So that's something else. Of course, we're still 3 weeks, a little under 3 weeks, so we have some time. So, free response question about experimental design and analysis. So this is probably one of those questions that's really, it's either you love it or you hate it, because what this question always has in common is you're always going to be asked a couple things. One thing you're always going to be asked for is to design an experiment, and designing an experimental procedure involves a couple components. So I'll give a couple tips here, because this is something that is in E&M too, and it is, I'll be honest, it is probably one of the most frustrating types of questions because you never know if you're too specific or you're too vague. So a couple of the key components here is, first of all, um, always include the equipment. Always include the equipment. Equipment and the measurements. Measurements have to be done with equipment. No equipment, no measurement. Second thing is equations. Write out the equations here because the equations are going to be what help you figure out what measurements need to take. And then repetition. Always include the aspect of repetition when you're describing an experimental procedure because this is something that applies not just to physics, but also statistics and experimental design in general. You want repetition of an experimental procedure so you can see a trend, because the trend is ultimately what you're trying to determine from the experimental data. So equipment measurements you're going to take, you're going to get those measurements from the equations that describe the scenario, and then you're going to get trend through repetition. Describe how the data will be collected is going to be more so what you're linearizing. What is being either linearized, calculated, something along those lines. So very often it's going to be graph a line, use the slope to tell you something, to extrapolate something. All right, so that's that. Then this part right here is probably the more familiar part that you see, is the one you've seen in past exams if you look at these before, the ones where you draw the line of best fit, although unfortunately now you have to actually do the graphing yourself. For the past couple of years, it's usually been you're just given probably because you only have 45 minutes, so you're just given given the dots and you just have to draw the line. This would probably be the one easy point that's always on the AP test. And you also need a ruler, keep that in mind. Let me close this tab. You always need a ruler for that. Make sure you bring a ruler to test day. I think that's still allowed, I'm pretty sure. So just double check with that. You're going to want to, so this next part of the question is going to be the more familiar part. Although what's going to be different now is you have to once again start with you're always going to want to start with a equation. You're going to want to manipulate it to find the slope. Find the slope and linearize. Because what's common about these types of questions is you're going to need to, using what you're given, figure out what you don't know. That's the whole point of linearizing and extrapolating data. So in this case, you're going to want to use things like, so this equation, let's see, what's the Yeah, so in this case, because we're looking at kinetic energy, we're looking at impulse, we're going to want to use things like conservation. We're going to want to look at conservation of energy. We're going to want to look at uh, impulse as a change of momentum, things like that. So remember to always, when you fill out this chart, so whenever you're always going to be asked to determine what the horizontal and vertical axis quantities are. That's what you get from taking an equation, manipulating it to find the slope, and then what you do is once you have those quantities, you're going to fill in the rest of the table with it and make sure you remember your units. One thing that's super helpful when it comes to manipulating the slope and manipulating the variables is to include units in your slope, because when you do that, you're going to have a it's going to help you assure that you're doing the math correctly, because when you end up finding the quantity that you want to find, what happens is you're going to graph all this stuff, you're going to draw a line of best fit using your equation, and you're going to be asked to find something. So in this case, you're being asked to calculate the value of the impulse. That's going to be somewhere from your slope. So the slope is going to be equal to something in terms of impulse, is what it's going to be. It's going to be some functional dependency of impulse, is what it's going to be. So yeah, this is one of the longer questions. This one takes a bit more time. Take your time on this one, because especially for the first couple parts, make sure you're going into enough detail about the equipment, the equations you're using, repeating it, and then how you're going to use that data to extrapolate the data. Or sorry, how you're going to use that data to extrapolate unknown data. Deriving equations, always, math is going to be your best friend with this type of question right here, and making sure that you're correctly representing it as you go along. Because remember, one of the things that you don't want to do in physics is just write down an equation and just use it blankly, because sometimes you have to manipulate quantities to make sure you're getting the correct representation. That's going back to translation between representations. I want to make sure that you're correctly translating between the physical visual representation that you're given and the mathematical representation that you're given.
Just to confirm what you said before, you are allowed to ruler straight edge, but yeah, only on the physics exam.
Yes. Okay. Awesome. Thanks. Yeah, I remember last year we were allowed to use it for physics. I think that was the one exam we were only allowed to bring it for. Thank you. All right. Last question, and then I think we'll wrap up. We'll take some questions if anyone has any, just so we have some, so we end off with clarity. So, qualitative and quantitative translation. This is a relatively short question. What's going to happen with this question is you're going to be, this one is focusing more so on using mathematical representations to justify intuition. So even though you're using physics intuition, at the core, you're going to still derive from mathematics. Now, for some questions, you're going to be asked not to use equations. So in this case, you're going to have to use conceptual physics ideas. For example, with this question, we're being asked about how fast do these things how long does it take for each of these objects to travel. The more the more inertia, obviously the more inertia something has, more gravitational potential energy is converted into rotational kinetic energy, all that stuff like that. So that's something to keep in mind. I'm just kind of blabbering at this point because it's been 2 hours and I'm getting kind of tired. But that's the whole idea: is to use intuitive but conceptually accurate physics when you're not being permitted to use equations. You can still write out equations. You just can't really use them in your justification. Like you can write them on, like, I think you'll have scrap paper. I'm not sure, but you know, I actually have no idea if scrap paper is a response because it's online this year. They're really weird about scrap paper because you back in the day you couldn't use it for the multiple choice, but now you can. It's wacky. security of questions, all that stuff like that is really wacky what College Board does, but whatever. So conceptually accurate physics is critical here. Then you'll be asked to use mathematics to show relationships between quantities. So this is where, this question type, yes, we're looking at different types of questions, but this question, sub-question type is pretty much everywhere. Like even in these old tests, derive an expression, derive an expression, derive an expression, everything is just derived. You get the idea. Derive an expression for quite literally everything. That is the great part about physics. And then once you have your equation from part B, part C is going to ask you to use that equation to qualitatively justify a particular claim. So again, using the quantitative aspect and the qualitative aspect interchangeably to support each other. So those are all the response questions. It's a lot. It's a lot to do in an hour 40 minutes, but it's definitely manageable compared to, like 12 pages of this stuff in 45 minutes with all that stuff. Comparison. This is 2 years ago. Last year's response questions were also pretty hard, but they were okay. That's the one I took it last year, so that's the one I did. No, this one was the year before. This is not the one I did. It was a different one, but this was the one I looked at to study throughout the year. So all in all, read the questions carefully, write everything out, because remember, partial credit is very much possible on the AP Physics test. Sometimes you might think, if you write this out, it might not help, but who knows, if you write just this one thing out, maybe you'll get a point just for writing it out, and that could be the difference between getting a 4 or 5. Who knows? So, all right, I know there's a lot of yapping, but reading everything carefully, understanding what they're asking you, and big things, know how to drive expressions, beware of functional dependencies, and make sure all of your representations, whether mathematical, graphical, physical, are matching each other and are consistent with each other. Alrighty. Yeah, I'm just looking at the chat now. Um, yeah, this is pretty much, yeah, ruler straight edge is practical, is best for calculating slope and all that stuff. Uh, yeah, physics one, physics two, yeah, yeah. All right, so that's pretty much the wrap of the session. Let's see, any questions? How do you find the slope in question 3? Let's take a look real quick. So the slope in question 3, well, what you're going to do is what we're going to end up doing, I'm not going to do it here in detail, but once you have your equation, you're going to take your vertical and horizontal axes. The vertical and horizontal axes are going to be expressions in terms of m and h and other constants. So you're going to end up plotting those points onto this graph right here, and then you're going to draw a line, and then using your ruler, you're going to calculate the slope. Oh, and something that's important, when you calculate the slope of the linear regression line, do not use the points that you get from the chart. Only use points on the line. Sort of thing. Only use points on the best fit line, not the data points. Not data points. Because they will not give you full credit if you use data points and not the points on the line. So keep that in mind. Ooh, 7 APs, that's a lot. Yeah. Best of luck. Yeah, it's a curve wise, that's a good question, because here's the thing, right? I mean, in past years, I mean, according to Albert IO, it's been like you need a 50 something to get a 5, I think. But It could be, I mean, it could be higher or lower. I think it depends on the year. I mean, for physics one, it's higher. I remember that for sure. But it changes with every single exam. But with the way the equating process works, I mean, it's not like it's not graded on a curve. It's graded by equating. So yeah, I would think it would probably be higher this year, given that the timing is not as strenuous. Because if you look at the average scores in the first response questions in past years, you'll see that they're like some of them are like a big amount of them are less than 50%. I've seen quite a few that have an average back when they had the 15-point per response questions. I've seen quite a few questions that had average scores of like less than the 20%, which is yeah, physics C mechanics has so yeah, physics C mechanics has that. Yeah, algebra 2. All right, anyone else have any questions on anything physics related, anything general? Physics 1. I did not take physics 1. Our school doesn't offer physics 1, but we do have physics honors, although I also kind of skipped that. I just went into AP physics. But because I took calculus the year before, because I took calculus in sophomore year, so in junior year I started straight up just on AP physics.
What is your school letting you do that?
Uh, course acceleration, all that
And
kind of
this is the
stuff.
first time they're letting.
Yeah, I mean, there's different paths that you can take with the physics and the calculus sequences. But this exam in particular, yeah, physics. I mean, here's the thing: physics is it's a hard subject, right? It is truthfully a very hard subject. I think out of all the APs I've taken, it's probably I would say it ranks probably like in the top three, maybe even like top two of the hardest exams I've taken. I mean, with this exam, with the physics exam this year, when it comes to studying for the physics exams at this point, you know, do as much practice as you can, especially if you've already covered all the content. If you have, if there's content that you haven't covered yet, but try to cover it. But at this point in time, practice questions are going to be very important for preparing because the more you do, the more you'll see how the style of the style of questions kind of has patterns over time, and you'll see that. You'll see the patterns of questions over time, and let's say on exam day. I mean, as hard as it sounds, take a moment, relax, and just make every single step and move intentional. That's what I'd say. So let me see. Let me see. Chat. Any question? I would say yeah. It is definitely still yeah. I agree. It is definitely still good practice because you're still doing physics. The timing might. I mean, here's the thing. Honestly, even if you're even if you're training for the old timing, it could even be better because if you can do 35 multiple choice in 45 minutes, you can definitely do 40 multiple choice in 80 minutes. Sure, the questions might be a little bit harder, but if you're training on a time scale that's way harder, when you get to that easier scale, it'll be much easier. So yeah, the past exams are definitely still good to do. It's still physics. You're still doing physics. The content scope hasn't changed. It's just that the way they ask the questions is a little bit different, but all the skills are still the same. Similar, yeah, similar wording. Yeah, definitely a good idea to do past questions. Pathfinder. What is Pathfinder? Oh, yeah, fluids. They added that to the AP Physics 1 exam this year. Uh, I like looked at a couple of videos on fluids, and I'm like, I was just like, yeah, I didn't feel like I didn't feel like doing fluids. Fluids is like super wacky. Difficulty. This exam is easier. I would say the difficulty is probably like about the same. I would say, question wise, because they're still asking you like, in my experience, when I took the AP Physics test last year for mechanics, when I did that last year, it was quite something, but not that much tedious computation. A lot of um, a lot of conceptual questions still, just like the ones we saw today. So I'd say the difficulty of the questions is probably roughly the same. So yeah, that's again, but that's just an opinion-based thing. It's not a objective thing. Difficulty will be to your up to your interpretation. Yeah, I have a lot of tabs open. That's kind of just how I operate. Don't mind that. uh, eh, yeah, I think whenever I screen share or wherever I show my computer to someone, the first thing that gets noticed is just the fact that I have like 70 tabs open. But um, I have no idea because I did try I actually did try looking for some on YouTube yesterday. I saw them in AP Classroom, but I saw them in AP Classroom, but they weren't. I didn't see them on YouTube yesterday. Um, they'll probably be released on YouTube at some point. Uh, computer with NASA. No, I don't. I do not share my computer with NASA. Yeah. Okay. Yeah. But anyways, back to the actual physics question. Does anyone have any physics related questions? I mean, we had a couple about exam strategy. We did have a
Guys,
couple.
don't bully DF or he's not gonna come back.
I got two more sessions I'm hosting. If bullying means no more
DF, I
two
don't
sessions.
know bro's name.
Yeah, you can call me DF. It's fine. I go by a bunch of online names. I got one of my nicknames in other servers is Gradient because that's what this thing is. It's the gradient vector. It's okay. It's okay. You're all good. I'm going to be co-hosting AP Chinese with someone else, and I'm also doing music theory, which I did last year too, actually. So yeah, yeah. Gradient vector is awesome. Calc three is fun.
How many APs did you take? Jeez.
Wait, does it say? Oh wait, you can see the APs I take. Hold on. Oh, did I add the role or something? Wait, does it say that? Or
So no, you want to take over again?
see, well, I'm looking at the fluids questions. I'm not gonna lie. I mean, fluids isn't on the C mechanics test, so I don't really know fluids. I'm not gonna lie. Anyways, yeah. Any actual other questions about any other? Just so you know, this is all still recorded.
Yeah, I just have like a general question.
Yeah,
Um, is the real difference between just AP Physics, just like the math applied and like the complexity difference? Because a lot of it's very, very similar to like regular
like physics one.
physics. No, like just plain physics, not anything AP, just is it physics one? I have no clue.
And uh, and if we're looking at the differences between like physics one, physics two, physics C's. I mean, yeah, the physics C's, both mechanics and E&M, they rely on they're calculus-based physics courses. Physics one and physics two are algebra-based physics courses. And I mean, it's not that there's not that much of a difference, I think, between just the AP physics courses and general physics courses. I mean it's college level physics. If that makes sense. I mean AP curriculum
Yeah.
is based on college curricula and pedagogy, but I think does that answer your question?
Yeah, thank you.
Yeah, of course. Rotational motion practice. Oh, recording will be. I'm gonna upload it to YouTube and post it as as a unlisted link, and I'll share that with the admin. Uh, rotational motion practice. Let's see if I have any rotational motion practice. See if I can find any rotation. Um, um hold on, let me answer these conceptual questions first. Physics one. See, I mean, I haven't taken physics one yet, but going into physics one of the big things, definitely make sure your foundation with math is strong because physics one does rely on a lot of just general algebra and also trigonometry. Make sure you have that ingrained in you. That in general. Basically, with physics one, it's kind of you're just starting, you're building from the ground up, so there's not too much like pre-course work to prepare for. It's mainly the math, mainly the algebra. You have to be more to be strong with algebra in that context, as well as the trigonometry aspect of it, which is kind of part of algebra. But yeah, Calc 3, honestly, um, for mechanics, honestly, Calc 3 isn't that isn't particularly helpful. But for E&M, for electricity and magnetism, I have found Calc 3 to be somewhat conceptually helpful, but it's not an expectation of the course to know Calc 3. So, I mean, if you know Calc 3, obviously it's good. You know, it's definitely helpful, but it's not mandatory per se. Difference between, translational, rotational kinetic energy. Good. That's a good question. So, yeah, that's exactly what it is. So, translational kinetic energy is the calculation of kinetic energy by multiplying 1/2 m times the velocity of the center of mass. That's the big distinction. When you have a when you have a let's say a rolling ball, you have when you have a ball that's rolling, the center of mass is moving, which gives you rotational, translational kinetic energy. The ball rolling is rotational kinetic energy because you have mass that's rotating about an axis of rotation. So that's rotational kinetic energy. If you have a ball that's just sliding across the ground without rolling, the center of mass of the ball is moving, yes, but it's just sliding along. So there's no rotational kinetic energy in that circumstance. That makes sense. So yeah, kinetic, yeah. So yeah, that's rotational. The kinetic versus rotational kinetic energy. It's the distinction between the rotation of mass around an axis of rotation versus just the translational velocity of or translational speed, really, of the center of mass. And I say speed because 1/2 mv squared, you're going to get kinetic energy is always going to be positive. It's not going to be negative. So it's going to be speed. It's going to be speed squared, not velocity squared. General advice for FRQs, as I was saying earlier, first of all, read the questions very carefully because AP Physics, as I love to say, they love slapping paragraphs in your face, which is really annoying. But um, make sure you read the questions carefully. That is a big thing with FRQs. And as I think one other thing I was saying earlier is always make sure your representations, whether it's make sure your graphical, mathematical, and any qualitative representations you have are are consistent with each other. That's a big thing because that's going to help you check your answers to make sure they're all consistent with each other, and make sure they make sense logically. So yeah, read through each question carefully, do it one step at a time. And oh, another thing, one other thing with FRQs, especially with these multi-part FRQs, if you're stuck on part A, don't just skip to the next question. Let's say you're on question 1A and you're stuck, don't just skip to question 2. Give part B a try because most of the time the parts in an FRQ are not going to be dependent on each other. They're more so for physics, they're a little bit more dependent on each other, but always give every single part of the problem a try before we keep going. Because sometimes because also one thing you get is you do get continuation credit if you even if you derive an expression wrong, for example, in like part B, if your reasoning and logic is consistent in part C, you'll get some continuation credit, even though you might not get the final answer point. Oh, that's a lot of questions in 25 minutes. That sounds calculus skills primarily differentiation and integration. You don't need to know how to do limits, but you should at least conceptually understand limits. Um, Definitely be able to differentiate polynomials, trig functions, know how to integrate polynomials, like stuff like that. Yeah. Now we have a color battle in chat. It's
Guys, I
okay.
think the best color is yellow.
Yeah.
I'm gonna get flamed so hard. Wait, watch this.
Yeah. Then do keep in mind that there is a calculus formula sheet on the AP Physics formula sheet. Let's see if we can find the one from well, this is what it used to look like. This is what it used to look like, but it looks similar now. So I mean, the better you know calculus, the better. Okay. Uh, yeah. I've honestly for like a good amount of time just been just been kind of answering questions. Yep, of course. Let's see. Okay. Are there any other? Oh, yes, I can definitely post the PDF of stuff. Yeah, that'll definitely be posted. I'll connect with the admins about posting that. But yeah. All right. Any other questions? Last minute questions. I mean, it's been almost 3 hours, but it's okay. It's okay. What is a solid angle? Solid angle. I've never heard that piece of nomenclature before. A solid angle. I mean, you have linear displacement, and you can also have angular displacement. Um, Solid angle. I'm not sure what that. It might be a different piece of nomenclature. Is there like do you have like a rough description for what it might mean? Angle inside a cone. Um, yeah, I mean it's you don't have to know it for the AP Physics test, so I don't think you have to worry about that. Simple harmonic motion, circular motion. Oh, let's see. Okay, okay, we're connecting representations. Oh, this is good. Give me a second. Let me think. Simple harmonic motion, circular motion. I mean, they're both periodic. That's one thing that's for sure. Simple harmonic motion, a key distinct feature that's important is restoring force is dependent on the restoring force is dependent on displacement from the equilibrium position. Simple harmonic motion, whereas with circular motion, the force, if you have uniform circular motion, the force is always directed towards the center of the circle, the centripetal force. So, I mean, they're related in the fact that they're both periodic, but uh, yeah, simple harmonic motion. Yeah, there's a good chance. There's a good chance it could be on an FRQ. It will definitely not be the entire focus of an entire FRQ, but you might need to, for example, know the differential equation for simple harmonic motion, like using Newton's law, get a differential equation for that. But simple harmonic motion, yeah, I can definitely see it being asked on an FRQ. Yes, an FRQ, yep. Yeah, all right. All right, I think we can, yeah, we can, one last chance, one last chance for final questions. And then then we're gonna cut this off here. Yep, of course. Of course. Alrighty, that is going to be all for today then. Um,
Thank
yeah,
you so much.
yeah, of course. Of course. Yep. You're welcome, everyone. Dab it out. Try as a gem. Let's see, try as a gem. Multiple string systems. If you have springs in parallel, let's see. Springs in parallel, I think means a higher. I believe springs in parallel means a higher value of k or horizontal. You know, spring more. Um. Also, yes, I did say dab in 2025. It's a meme I've been carrying on for like many years at this point. Um. I think multiple springs to block vertically. Um. It's okay. It's okay. Trying to think. You have when you have multiple. I think because the more springs you have in parallel, the more resistance there is. Right. I'm trying to think because this is a lab we did last year actually. Spring is attached to a block when you apply force. Oh, spring is attached to a block and we apply force on it externally. In that case, you would have a restoring force from the spring because that's Newton's third law. But I think that's what it means. Rap battle. Yeah, I think what you're asking is what happens to a block on a spring when you apply a force externally. In that case, the thing would just be you would have a restoring force from the spring by Newton's third law. I hope that answers your question. But all right, we're locking in for AP Physics. Yeah. All right, yeah, I think that's all then. All right, well, thank you everyone for coming. Hope you found this helpful, even though it was a lot of yapping, but review sessions kind of are yap. Yeah, of course, of course. Alrighty. Yep, of course, of course. Alrighty. All right, thanks, guys. Yeah, dab it out. Alrighty. That will be the end of session then. Alrighty. See you later. I'm gonna end the recording.